Namaste to all. Hope all of you might have watched my previous video, Surface Chemistry Part 1 Absorption. As I told you earlier, the next feature of surface chemistry is catalysis. Potassium chlorate, when heated strongly, decomposes slowly, giving dioxygen. The decomposition occurs in the temperature range of 653 to 873 Kelvin, as you can see here in the equation. The catalyst used is manganese dioxide. However, when a little of manganese dioxide is added, the decomposition takes place at a considerably lower temperature range, that is 473 to 633 Kelvin, and also at a much accelerated rate. And the catalyst, that is manganese dioxide, remains unchanged in mass and composition after the reaction. So what is a catalyst? What is the phenomenon of catalysis? A foreign substance that changes the velocity of a chemical reaction without being used up in that reaction is known as catalyst, and the phenomenon is catalysis. Or substances which accelerate the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalysts, and the phenomenon is known as catalysis. So this is a sentence written in your NCERT textbook. Some other examples of catalysis is hydrogenation of alkenes in presence of nickel, palladium, platinum as catalyst, which you have learned last year. The hydrolysis of sugar to form glucose and fructose, the catalyst used in this equation is H+. Catalysis is of two types, homogeneous catalysis and heterogeneous catalysis. What do you mean by homogeneous catalysis? It's when the reactants and the catalyst are in the same phase. For example, sulfur dioxide combines with oxygen in presence of NO to form SO3. Here, the catalyst and the reactants and the products all are in the gaseous phase. And that type of catalysis is called homogeneous catalysis. Here, SO2, like you can see here, SO2, oxygen and NO are in the gaseous phase. There are many similar reactions given in your textbook. Hydrolysis of ester to form acid and alcohol. The acid is used as a catalyst. Here, the ester, the water, the products formed, that is the acid and the alcohol plus the catalyst, that is HCl, all are in the liquid state. Hydrolysis of sugar also to form glucose and fructose in presence of H+. That is, here we are using sugar solution. The product formed is also glucose and fructose is also in the solution phase. The catalyst uses H2SO4. That is also in the liquid state. So this is another example of homogeneous catalysis. Heterogeneous catalysis, you can easily find out what is heterogeneous, because if you know homogeneous, heterogeneous is very easy. When the reactants, the products and the catalyst are in different phases. That is, in this reaction, the formation of ammonia example is given. Nitrogen, hydrogen combines to form ammonia. The catalyst is iron. Here nitrogen, hydrogen and ammonia are in the gaseous state when the catalyst used is in the solid state. Reactants in the gaseous state, while catalyst is in the solid, solid phase. Reactants and catalysts are in different phases. That is heterogeneous catalysis. So homogeneous, when the reactants and the products and the catalysts are in the same phase, while in heterogeneous, the catalysts, the reactants and the products will be in the different phases. Types of catalysis. The different type of catalysis. This is not given in your NCERT textbook, but you can simply understand that positive catalysis. From the word itself, you can easily understand the catalyst that increases the rate of a reaction is called positive catalysis. Example is given here, sulfur dioxide plus oxygen forming sulfur dioxide, NO. It increases the rate of a reaction, so this comes under positive catalysis. Negative catalysis, from the word meaning itself, it is clear. The catalyst decreases the rate of a reaction. So in this case, oxidation of chloroform, CHCl3 is chloroform, oxidation of chloroform to form COCl2 plus chlorine plus water. Here ethanol acts as a negative catalyst. Autocatalysis. Autocatalysis is, there is one question based on autocatalysis in your text question. When one of the products itself is acting as a catalyst in the reaction, that phenomenon is called autocatalysis. When one of the products itself act on the catalyst, it acts as a catalyst in the reaction, is known as autocatalysis. There's a titration next year. It's the 12th standard. You have in the syllabus the titration of potassium permanganate against more salt and potassium permanganate against oxalic acid. In both the titrations, autocatalysis is acting. The titration of oxalic acid against acidified KMnO4, the decolorization of the KMnO4 is slow in the beginning. That is, when you are adding KMnO4 is usually taken as the burette and oxalic acid or more salt is pipetted out. So in that case, in the beginning, we can find the decolorization of KMnO4 is very slow, but it becomes faster after some time. Why? Because during the titration, Mn2 plus ions are formed, and this Mn2 plus ions formed act as a catalyst, and hence Mn2 plus ion is an example of an autocatalyst, and this is an example of autocatalysis. Here Mn2 plus acts as an autocatalyst. This is there in your textbook. What are promoters and poisons? Promoters are substances that increase the activity of a catalyst. Molybdenum acts as a promoter for iron catalyst in Haber's process for manufacture of ammonia. Nitrogen and hydrogen combines to form ammonia, and the catalyst, as I had discussed earlier, catalyst is iron. But we also use molybdenum because it acts as a promoter, because it increases the activity of the catalyst ion. Catalytic poisons. From the word meaning itself, it is clear what is it. Poisons decreases the activity of a catalyst. Next is adsorption theory of heterogeneous catalyst. Adsorption theory of heterogeneous catalyst. According to the old adsorption theory, the reactants get adsorbed on the surface of the catalyst. This increases the concentration of the reactant. Also, energy is given out on heat of adsorption. The increase in concentration and the heat energy achieved increases the velocity of the reaction. This is according to the old adsorption theory. That is, the reactants are adsorbing on the surface. As a result, the concentration increases. When it is adsorbed, more of the reactants will be there nearby, and this increases the concentration and the velocity increases. Second theory is according to intermediate compound formation theory. The catalyst combines with the reactant at one stage to form an intermediate. The reactants will combine with the catalyst, and intermediate is formed first. This intermediate later on decomposes to give the product and the catalyst. That is, catalyst will be obtained chemically and quantitatively unchanged. This is what we had learned earlier. Now, the modern theory is a combination of old adsorption theory and intermediate compound formation theory. It's very easy to learn also. The catalytic activity takes place on the surface of the catalyst. So, all the reactions take place on the surface of the catalyst. There are 5 steps involved in the adsorption theory of heterogeneous catalysis. Step 1, very easy. We can find here, this is a catalyst here, that one drawn in circles is a catalyst. The reactant is A and B. So here it is of A and B is combining to form products, and a catalyst is present. How is this step taking place, and what is the adsorption theory is what we are going to discuss. In this one, you can find reactant molecules. First step is reactant molecules diffuse to the catalyst surface. They will diffuse to the catalyst surface. Step 2. Step 2 is reactants, that is A and B reactants, are adsorbed on the catalyst. A and B separately adsorbed. Step 3, you can find the A and B, there is a bond being connected. There is an intermediate is formed. Chemical reaction takes place. A catalyst is there, A and B. So this is an intermediate that is formed. And in the next step, after an intermediate is formed, the desorption of the product takes place. The product is removed from the catalyst. What is desorption? We have learned in the adsorption part, the removal of the adsorbate from the adsorbent. So here the desorption is taking place in the 4th step. In the 5th step, product diffuse away from the catalyst surface. After desorption, diffusion is taking place. And the surface now is free. That is, the catalyst surface is now free to absorb more reactant molecules. So this theory explains how catalyst remains unchanged in mass and chemical composition. The theory does not explain the action of catalytic promoters and catalytic poisons. So the first step, the diffusion of reactant molecules on the catalyst surface takes place. In the second step, step 2, the reactants are adsorbed. In the step 3, an intermediate is formed. In the step 4, the desorption of the product is formed. And in the step 5, the diffusion of the product from the catalyst surface is taking place so that more reactant molecules can adsorb on the catalyst. Next is very important, the important features. The heading is important features of solid catalyst. The two important features of solid catalyst is activity and selectivity. Very important question also. What do you mean by activity and selectivity of a catalyst? It has come for the board exam many times. Also, it is there as a question in your textbook. So, the two important features, once again repeating it, it is activity and selectivity. What is activity? The activity of a catalyst depends upon the strength of chemisorption to a large extent. That is, the reactants must get adsorbed reasonably strongly on the catalyst to become active. It should get adsorbed, but it should not be, the adsorption should not be too strong. That is, if it is adsorbed so strongly, then it will get immobilized and other reactants are left with no space on the catalyst surface for adsorption. So what is activity? What is activity? If you have to say like this, activity of a catalyst depends upon the strength of chemisorption to a large extent. The reactants must get adsorbed reasonably strongly on the catalyst to become active. But the adsorption should not be so strong that they are immobilized and other reactants are left with no space on the catalyst surface for adsorption. Hope it is clear to you what is activity. This is very important. Selectivity. The selectivity of a catalyst means it's the ability to direct a reaction to yield a particular product. That is, a given substance can act as a catalyst only in a particular reaction and not for all the reactions. It means that a substance which acts as a catalyst in one reaction may fail to catalyze another reaction. So hope it is clear to you. Some examples we can find here. The reactants are carbon monoxide and hydrogen. The second reaction also, there is the reactants are the same, carbon monoxide and hydrogen. The third also, it is carbon monoxide plus hydrogen. The reactants are same, but the products will change if the catalyst is changing. The first equation, nickel is the catalyst. The product formed is methane and water. In the second one, copper, zinc oxide, chromium trioxide is used as a catalyst. The product changes to methanol. In the third one, copper is used as a catalyst. The product formed is formaldehyde. So that is why I told you earlier, a given substance can act as a catalyst only in a particular reaction, not for all the reactions. And the selectivity of a catalyst means it is the ability to direct a reaction to yield a particular product. Very, very important. A catalyst is selective. A substance that that catalyzes a particular reaction may not catalyze another reaction. I had told you just now. Next, very important feature of catalysis is shape, or different type of catalysis is shape selective catalysis. This is also another important part in surface chemistry. The catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and product molecules is called shape selective catalysis. That is, this type of reaction depends upon the pore. That is, if a catalyst is there, if it is having pores, it depends upon the pore size of the pore structure of the catalyst and the size of the reactant and product. That is, the best example of shape selective catalysis is zeolites. What are zeolites? Zeolites are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminium atoms, giving aluminium oxygen silicon bond framework. The last year we have learned zeolites. Zeolite is an example of a shape selective catalyst or shape selective catalyst. The zeolites has a honeycomb-like structure and it has pores in it. The pore size can be varied and the reactants will enter through the pores of the catalyst zeolite. All the reactants will enter inside, the reaction will take place, the products will be formed and these products will come out of the pore of the catalyst. And that is why we are saying the catalytic reaction, this reaction depends upon the pore size of the catalyst. The reactant has to enter through the pore of the catalyst. And once the product is formed, if the product size of the product particle is greater, it cannot come out of the pores of the zeolite. So it depends upon the size of the reactant and product, also upon the pore structure of the catalyst. Zeolites, aluminosilicates, what are zeolites I have mentioned, are widely used as catalysts. The application of zeolite is also important, used as catalysts for cracking of hydrocarbons. That is one example. Another zeolite, an important zeolite catalyst used in petroleum industry, ZSM5. You can refer your textbook, it's clearly given. ZSM5, zeolite, ZSM means zeolite C with microporosity 5. The porous size might vary. This ZSM5 converts alcohols directly into petrol by dehydrating them to give a mixture of hydrocarbons. So, what is shape selective catalysis? Give an example and an application or use is a very important question. Next, we'll go to the next part of surface chemistry, enzyme catalysis. What is enzyme catalysis? What are enzymes actually? The biology students might be knowing that enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of high molecular mass and forms colloidal solutions in water. They are very effective catalysts. They catalyze numerous reactions, especially those connected with natural processes. Numerous reactions that occur in the bodies of animals and plants to maintain the life processes are catalyzed by enzymes. The enzymes are thus termed as biochemical catalysts and the phenomenon is known as biochemical catalysis. Enzymes, as I had told you earlier, enzymes are protein molecules produced by living plants and animals. Examples of enzyme catalysis. The hydrolysis of urea. The enzyme used here is urease. Urease is an enzyme catalyst which is used for the hydrolysis of urea. Hydrolysis of sugar to form glucose and fructose. The enzyme used is invertase. Again, C6H12O6 on hydrolysis to form ethanol and carbon dioxide. The enzyme used is cymase. Milk to curd, lactobacilli enzyme present in curd is used. Proteins to amino acid. The enzyme used is pepsin. That is, in stomach, Pepsin enzyme converts proteins into peptides, while in the intestine, the pancreatic trypsin converts proteins into amino acids by hydrolysis. There is one more example given in your textbook, conversion of starch into maltose. The enzyme used is diastase. So please refer the textbook together with this video. Next is mechanism of enzyme catalysis. So next is mechanism. That is also clearly given in your textbook. The enzyme substrate. Substrate means a reactant. Relationship is just like a lock and a key relationship. Just like a lock key fits into a particular lock, the reactant molecules fit into the cavities of the enzyme. The intermediate is formed and later on the products are removed. An intermediate is formed which decomposes to give the product. So the reactant combines with enzyme and an intermediate is formed, and then from the intermediate the products are formed. As you can see here in this picture, there is a reactant given in the blue color, that is a substrate. The enzyme, which is called the catalyst, in the orange color, and the enzymes have active sites on it. The enzyme and the substrate and the reactant will come closer, that is, they will get bonded. And later on, after the intermediate, that is the complex is formed, this is the intermediate form. This intermediate will decompose to products, and the enzyme is a catalyst. If you get back the enzyme chemically and quantitatively unchanged. So the steps are given. In the first step, you can see the enzyme and the reactant. Reactant is a substrate, so that is why S is written here. They combine to form an enzyme substrate complex is formed here. In step 2, the enzyme substrate complex formed will get converted to a complex, activated complex. And this activated complex will get converted to the product and the enzyme. So you get back the enzyme. Hope this is clear to you. Next, very important. What are the characteristics of enzyme catalysis? Characteristics of enzyme catalysis. The first characteristic is highly specific. Each enzyme is specific for a given reaction. One catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyze the hydrolysis of urea only. It does not catalyze hydrolysis of any other amide. The example is given here. So first one is it's highly specific in nature. Second one, it is highly efficient. One molecule of an enzyme may transform 1 million molecules of a reactant per minute. So it is that fast, and that is why we say it is highly efficient. One molecule of an enzyme can catalyze 1 million reactant molecules. Next feature or next characteristic is highly active under optimum temperature. Highly active under optimum temperature. That is, the rate of an enzyme reaction becomes maximum at a definite temperature called the optimum temperature. On either side of the optimum temperature, the enzyme activity decreases. The optimum temperature range for enzymatic activity is 298 to 310 Kelvin. And human body temperature being 300 Kelvin is suited for enzyme catalyzed reaction. So here you can find a graph which is not there in your textbook. Enzyme activity increases, and at a particular temperature it becomes maximum. Usually optimum temperature ranges from 298 to 310 Kelvin, which comes under the body temperature, which I mentioned earlier. Enzyme activity is maximum at optimum temperature. Similarly, highly active at optimum pH also. The rate of an enzyme catalyzed reaction is maximum at a particular pH called optimum pH, which is between pH values 5 to 7, which is also under our body temperature. So usually the range is 5 to 7 pH. Enzyme activity is maximum at optimum pH. The next characteristic of enzyme catalysis is increasing activity in presence of activators and coenzymes. What are activators and coenzymes? The enzymatic activity is increased in the presence of certain substances known as coenzymes. So earlier we have learned promoters, just like promoters. These substances will increase the activity of the reaction. These are called coenzymes. It has been observed that when a small non-protein, which is a vitamin, is present along with an enzyme, the catalytic activity is enhanced considerably. Activators are generally metal ions such as Na+, Mn2+, CO2+, Cu2+ ions, etc. These metal ions, when weakly bonded to enzyme molecules, increase their catalytic activity. Amylase in presence of sodium chloride, that is Na+ ions, are catalytically very active. So once again repeating it, activators and coenzymes contain metal ions like Na+, Mn2+, CO2+, Cu2+, etc. weakly bonded to enzyme molecule, which increases their catalytic activity, and these are known as activators. Enzymatic activity is increased in presence of certain substances known as coenzymes. Next is inhibitors and catalytic poisons. Like ordinary catalysts, enzymes are also inhibited or poisoned by the presence of certain substances. The inhibitors or poisons interact with the active functional group on the enzyme surface and often reduce or completely destroy the catalytic activity of the enzymes. The use of many drugs is related to their action is enzyme inhibitors in the body, which you'll be learning in detail in the last chapter.